the discovery hidden inside random noise. At first, it looked like nothing, just static, errors, background interference, the kind of data scientists are trained to ignore. For generations, randomness was treated as absence, the absence of signal, the absence of meaning. Noise was what remained after understanding failed. It was filtered out, averaged away, discarded so the real pattern could appear. To understand why that assumption collapsed, we need to revisit how science learned to trust order. Measurement improved by eliminating variation. Precision meant control. The cleaner the signal, the closer we believed we were to truth. Randomness became the enemy. But as instruments grew more sensitive, noise refused to disappear. Even in perfectly controlled environments, fluctuations remained. Thermal motion, quantum uncertainty, statistical jitter. The universe, it seemed, would not sit still long enough to be measured cleanly. At first, these irregularities were treated as limits, boundaries of what could be known. But a few researchers began asking a different question. What if the noise wasn't hiding the signal? What if it was the signal? They began studying the patterns inside randomness itself. Not averages, but distributions. Not steady values, but fluctuations over time. And slowly, something unexpected emerged. The noise was structured. Certain variations repeated. Certain correlations persisted. The randomness was not uniform. It carried fingerprints. Subtle regularities embedded inside apparent chaos. This was the first reveal. What looked like meaningless fluctuation contained information no smooth signal ever could. The noise was sensitive to hidden dynamics. It responded to forces too subtle to register directly. When researchers stopped filtering it out, entirely new behaviors appeared. Systems revealed early warning signs before collapse. Tiny fluctuations hinted at upcoming transitions. What had once been dismissed as error turned out to be anticipation. The discovery hidden inside random noise was not loud. It was quiet, statistical, and easy to miss. But once seen, it cannot be unseen. Because randomness was no longer empty. It was speaking. And science was finally learning how to listen. As researchers refined their methods, the implications grew. Noise was not a nuisance layered on top of reality. It was woven into it. Systems did not behave despite randomness. They behaved through it. In biological systems, noise amplified sensitivity. Neurons use variability to detect faint signals. Genetic expression relied on fluctuations to enable adaptation. What appeared messy at the surface proved essential underneath. The same pattern appeared in physics. Quantum noise revealed virtual particles flickering in and out of existence. Thermal fluctuations exposed phase transitions before they occurred. Noise acted as a probe, revealing structures invisible to steady measurement. This led to a deeper reveal. Randomness carried memory. Not memory in the human sense, but statistical traces of past interactions. The noise profile of the system changed as the system changed. By reading those changes, researchers could infer history and trajectory without direct observation. This transformed prediction. Instead of forecasting based on current state alone, scientists began using noise signatures to anticipate shifts. Ecosystems approaching collapse, materials nearing failure, markets on the edge of instability. The noise grew louder before the break. At first, this seemed too powerful. Critics warned of overfitting, of seeing patterns where none existed. But repeated experiments confirmed the effect. When noise patterns shifted, outcomes followed. Then came the unsettling part. In some systems, noise did not just reveal behavior. It influenced it. Small fluctuations nudged systems between states. Random variation became a driver change, not just a reporter. Order emerged because of noise, not in spite of it. This reversed a core intuition. Stability was not the absence of randomness. It was the product of it. And that inversion set the stage for a deeper conflict. Because if noise shapes reality, then control is never absolute, and certainty becomes a fragile illusion. The conflict sharpened when scientists realized what this meant for prediction and control. If randomness shapes outcomes, then removing it does not produce clarity. It produces blindness. Systems engineered to eliminate noise became brittle. Without fluctuation, they lost early warning signals. Failures arrived suddenly, without preparation. In contrast, systems that tolerated noise adapted. They shifted gradually. They survived disruption. This pattern appeared everywhere. Financial markets that smoothed volatility collapsed without warning. Ecosystems stripped of variation lost resilience. Neural systems deprived of noise stopped functioning optimally. The attempt to perfect order introduced fragility. The emotional tension peaked as researchers confronted the paradox. Noise was not a defect in measurement. It was a feature of reality, one that carried information, flexibility, and adaptability. Then came the most unsettling discovery. In certain systems, increasing noise improved performance. Random variation helped escape local traps. It enabled exploration. It allowed systems to discover better configurations than any deterministic process could reach. This phenomenon appeared in evolution, learning, and optimization. Mutation, exploration, trial, error. Noise was the engine of novelty. The implication was profound. A universe without randomness would be static, frozen, predictable, but dead. Change required uncertainty. Progress required fluctuation. This forced a re-evaluation of certainty itself. Control was no longer about suppression. It was about balance. Too much noise led to chaos. Too little led to collapse. The systems that endured lived on the edge. Balance between order and randomness. The discovery hidden inside random noise was no longer just about reading data differently. It was about understanding how reality stays alive. And that realization pushed science toward a final, uncomfortable truth. The climax arrived with a reversal few expected. Randomness was never the opposite of order. It was its partner. The discovery hidden inside noise revealed that uncertainty is not something reality tolerates. It is something reality requires. Without fluctuation, systems cannot sense their own limits. Without variation, they cannot adapt before collapse arrives. Noise provides friction for change. It creates room for alternatives. It allows systems to test possibilities without committing fully. In this way, randomness becomes a form of intelligence. Not conscious, not intentional, but essential. This insight reshaped how scientists approach the future. Prediction shifted from certainty to probability. Control shifted from elimination to modulation. The goal was no longer to silence noise, but to read it. The resolution was quietly transformative. By listening to fluctuations, researchers could anticipate tipping points. By preserving variability, systems gained resilience. By respecting randomness, engineers designed structures that bend instead of broke. This matters now because modern systems crave precision. Algorithms optimize relentlessly. Processes are streamlined. Variation is treated as inefficiency. But in removing noise, we remove foresight. We trade adaptability for temporary stability. The lesson from noise is not chaos. It is humility. Reality does not promise certainty. It offers patterns that whisper before they shout, signals that appear only when we stop demanding cleanliness. The discovery hidden inside random noise was never about embracing disorder. It was about understanding that life, intelligence, and stability all depend on a measured amount of uncertainty. Remove it, and systems become blind. Listen to it, and they learn how to survive. The discovery